All right, it's kind of bittersweet at this one. This is our last video. I don't know why it says 90 down there. I feel like an idiot, but you know what? I'm not always the best at things. Anyway, this is our last video. This is the last video for gases, last video for Gen Chem 1. So we're about to wrap it all up. In this last bit, we're going to talk about real gases. And real gases is a situation where the ideal gas law does not necessarily apply. Okay. So let's think through this. Okay. This is a picture of van der Waals, and we'll get into van der Waals in a minute. Um, there we go. Okay, so near STP, so all this data is at STP, standard temperature and pressure, so hopefully you remember what that is. STP is, oh, come on, people. Can I not have one video where I don't mess shit up? Okay, so we'll just remember that STP is 0 Celsius and 1 atmosphere, standard temperature and pressure. Near STP, gases are nearly ideal. So this is a bunch of different gases looking at the volume per mole, which we figured out in another video is close to 22.4 liters. Okay, ideal gas is 22.41, and all these are relatively close. Okay, what this is doing when we use the ideal gas law is we are using assumptions from kinetic molecular theory to make this work. We are assuming two things. First, that the particles have no volume, okay, which is another way of thinking about that the particle volume is very, very small compared to the size of the container, okay? The other thing we're looking at is that there are no intermolecular forces, which means that when we say this, we're assuming that there's no intermolecular forces, so the molecules don't interact when they collide. So this is assuming that we have elastic collisions, okay? Meaning that the molecules bounce off of each other and they don't lose momentum. That momentum is conserved during the collision, okay? All right, so most of the time, under normal laboratory conditions, ideal gas law is fine, okay? But there are times when gases behave more like what we call real gases. This is at very low pressures, very low temperatures, excuse me, and very high pressures, okay? Let's take a look at some of that data. At a high pressure, what we see is now the particles act like they have volume. Okay, we're not talking 1 or 2 atmospheres. Look at this data. We're going 800, 1,000 atmospheres out here. Okay, so the ideal gas has a smaller volume than the real gas, in this case, argon. And the reason for that is you can only squish things down so far. As the pressure gets tighter and higher and higher and higher, the volume collapses, right? PV, right? Boyle's law. Right? As the pressure goes up, the volume has to go down. As the volume goes down, the particles get closer and closer together, and it gets less and less ideal, right? The particles can only squish so far. So it acts like now our particles actually have volume together, right? And our gas becomes less compressible, okay? Van der Waals, this is the same guy that talks about intermolecular forces. He was big in the gases as well. And van der Waals was studying real gases and came up with what I call fudge factors, the van der Waals fudge factors, for fixing the ideal gas law. Okay, the constant that we call B takes care of the volume issue. Okay, so really, if we're looking at the volume of our gas that's real is from the ideal gas law, nRT over P plus N times B. N is the same number of moles. Okay. B is a constant and B is known. So we don't have to stress about it, okay? If we go to low temperature, okay, then the particles start to act like they're intermolecular forces that are working. Our collisions are no longer elastic. So instead of bouncing off each other, our particles stick together, okay? When they stick together, they act like they are fewer particles than they actually are, because you literally have uh, two particles that were there and they collide and they stick together. Now they're acting as one particle. Okay. So the pressure at low temperatures, right? Low temperatures being, 100 Kelvin, means that our pressure is lower for the real gas versus the ideal gas, because the gases act like there's fewer particles. So if there's less particles in the sample, the pressure goes down. Okay. Van der Waals has a fudge factor for this, and we call it A. Okay. A is a constant number here. N is the moles again. V is the volume. And this is what the pressure would look like under non-ideal situations. Okay. What we can do to make our lives interesting is to take these two fudge factors and stick them together and make what's called the Van der Waals equation. Okay, Van der Waals equation says that the pressure plus its fudge factor, n squared A over V squared, okay, times V minus NB, that's its fudge factor, is equal to nRT. Okay, this is a big equation. It's hard to remember. This will be given. Okay, so you don't have to stress about that one. If we need A's and B's, they are given. This is a table from the book from a whole bunch of gases, and it tells you what we have here, A's and B's. So if we know A and B and we know the data, we can figure out, some other stuff in the Van der Waals equation. Okay, and this just works out to being a big algebra problem, right? Because you can imagine solving for volume or solving for pressure or solving for temperature, right? Given A and B and a bunch of gas data, you can do that. Okay. That's all I got on real gases. Um, right. So if you need me for anything, let me know. Um, I would say catch you next time, but this is the last one. So have fun. Let me know if you have any issues or concerns, and I'm here to help. I'll catch you later.